Hi guys, welcome back. Um, in this video, we will be tackling some practice. So, in this video, we will be trying to reverse engineer three binaries or three challenges. Actually, each one of them have either a flag or we have to um, bypass the authentication that have been installed on it. So the main goal of this video and the next video is to apply all the knowledge that we have learned along the way. So, before we try to solve any kind of problem or any kind of challenge, actually, you have to try them on your own. And just after trying on your own, you can just join me and try to see how I solved the challenge. So you can find all the challenges in the description. You can just download them. They are 100% secure and they are used for educational purposes. Yeah. So let's start with the first binary. So the first thing that we have to do is we have to try to check the file or the format of the binary just before trying to reverse engineer it. So the first thing to do is just running file. So let's try to run it on the challenge one. So it's actually an ELF, um, a 32-bit actually. LSB stands for Little Indian, which means that all the addresses will be in the first order. So it's statically linked, which means that all the libraries used for this binary are um, inside of it. And it's not script, which means that all the function names and symbols are clear for us. So let's try to run strings also, which can help us understand a little about. Maybe we have some stuff to do. So we have congrats, we have you failed, try again. It's example.assembly, which means I think this is the name of the assembly with message. Um, length with message, fail message, length, fail message. I think this is the length of the message. We have buffer and we have ebench. This is the name of the sections. We have also, I think those are labels. So I suppose this is a an assembled assembly, which means that it's just an assembled file. It's not a compiled one by, for example, GCC or G++ or any kind of compiler. So it's just a binary that has been assembled. So yeah, so let's try to run that. Maybe see the behavior of what is. So it's asking for some input. So let's say iron byte. So it's saying you have failed, try again. So the first thing that we have now, so this is just basically some preparation that we have done in this place. So just to understand um, the behavior of the binary from the outside. Maybe a good thing to do, guys, is actually try to manually debug the binary. What does debugging mean? So debugging actually, guys, is trying to running the binary, but not like the usual run that you do when you try just to run a simple binary. By running a binary, I mean we should know or we should just try to check the state of the registers while the binary is running. So to do that, we can use a simple tool in Linux that is available. You can just install it if you don't. It's called GDB. So all what you have to do if you don't have GDB installed in your Linux distribution is to do sudo apt-get install GDB, and I suppose it will be just prompting for you a prompt just to say for you yes or no, and all what you have to do is just say yes or install GDB on your computer. Now what's really interesting is that GDB can help us debug binaries. So to debug a binary using GDB, all what you have to do is just type in GDB and the name of the binary. So we will be debugging challenge 1. Okay, so I think now we are into GDB, and guys, there's one thing to mention in here. If you have installed the default version of GDB, you won't be having all these colors that I have and this GIF sign. So GIF, guys, is a kind of extension that I have installed from the internet that can help me make my GDB more efficient. So to install GIF, all you have to do is go into here. This is GIF GDB install. And once you have that, you should just check that out. Yeah, and you just have to use this link just to install it. So it's pretty easy. Just you have to see the steps to install it. You have to do that and that. So it's pretty easy. You can just do that. Another thing to do is you have also to check that before I forgot, which is the GDB cheat sheet. So GDB cheat sheet is actually really helpful because GDB is actually a tool, so it has commands. So we'll be trying to tackle them together. So yeah, let's go back. So now we are in GDB, and the first thing that we have to check is what are the kind of functions that are available in this binary. By functions, I mean, for example, the main is a function. If you remember from the previous video, the sum was a function. So to see all the functions in GDB, all we have to do is just type in info functions, and it will be giving you some informations about the functions available in that binary. So we have, for example, the underscore start, underscore loop, print, fill, win, exit. So let's try to see the start since it's the door of the binary or the beginning of the binary. So to see the assembly of a function, we use the keyword or the command disassemble. So disassemble can help us disassemble any kind of function that is available. So to do that, you either have to give the name of the function, which is in our case the underscore start, or you could give him the address of the function. So for example, we could give him that. Um, okay, so let me just yeah, okay. No functions. Okay, I think we will be just giving the name of the function. Yeah. So this is actually the disassemble or the assembly of the function underscore start. So I suppose if you remember, we have run the binary and it prompt for us a place us to type in some characters, and it was just saying, I think it is failing and we have to try again. I don't remember. Let me just try to enter again. Desktop videos challenges. Okay, so we have this challenge. So it's saying you failed. Try again. So you see, guys, when we have tried to run the binary, it was saying like we have failed. Try again. So the main goal of this challenge is to understand the binary and try um, to see how it's exactly behaving. So let's start by debugging. So to debug, guys, we need to set a breakpoint, and the term breakpoint is a kind of famous because even if you have tried to debug, for example, even in high level code, for example, using I don't know, code blocks, WebStorm, or any kind of IDE. Actually, debugging is the process of just understanding where the bug is coming from. But in this case, we are trying to debug to see what is exactly the content of the registers while the program is running. So to do that, we have to set a breakpoint. So we can set a breakpoint in the underscore start and go from there. So we are now having a breakpoint at that address. Now, what's really interesting, we can see the informations about the breakpoints that we have been putting just using the instruction or the command info breakpoint. So info break. So it gives you the informations about the breakpoints that you have. So for example, let's suppose I want to have, for example, another breakpoint and at this address. So just one thing to mention, guys, that those are the addresses, or those are the virtual addresses that I have been talking about. If you remember the video about paging, so basically this is the instructions that the instruction pointer will be having, and those are the instructions that will be translated using the MMU, which is the memory management unit, if you remember the video of the paging. If you don't remember that video or you haven't watched it yet, you can just check it out if you want. So yeah, so let's suppose I will be having a breakpoint at this address. So this address I will be setting a breakpoint, and if I try to see now info breakpoints, or EB, just as a little abbreviation, um, we will be having two breakpoints. The first breakpoint and the second breakpoint. Now, if I want to delete a breakpoint, all what I have to do is just set delete two, for example. And if I do info breakpoint, it's gonna say to me that there is only one breakpoint remaining. So this is how you set breakpoints and you delete them. And you can check more out in the cheat of the GDB, which is I will be trying to put in the description too. So now what's really interesting is now that when we try to run the executable using the run, it's actually gonna be prompting to us this arrow, which is gonna be pointing to the current instruction that the CPU is going to execute, and a bunch of informations about the memory. So this place is gonna be the stack. So as you can see, so this is the stack, and this is the top of the stack that the ESP or the stack pointer is pointing to, and those are informations or some kind of arguments that have been passed to the stack before the binary was run by the exec VE syscall, if you remember from the video what I have tried to explain to you how the program execution is done by your operating system. So we also have in here the registers, which are the registers, the general purpose registers that they have told you about in the previous video. And in this place we have the E flags, which are the zero and the carry and the party and the HS, etc, 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 of the different kind of flags that can be set by the comparison, by the compare, I'm sorry, and by the test instructions. We also have the CS, the SS, and the DS, and the ES, and the FS, and the GS, which are a kind of segments that also exist in the assembly 86. What else do we have? So yeah, so whenever you have a color that is um, so those colors actually also help as um, just distinguish a string from a stack, from a heap, from the code, from a modified registers. As you can see, Jeff is really, really helpful when it comes to just dealing with GDB, and just adding Jeff to your GDB might just facilitate your life. Yeah, it will make your life easier. Yeah. So now we are at this instruction. So it is saying like it is going to move 3 into the EIX, and then it's going to move 0 into EBX, and then it's going to move some address into ECX, and then it's going to be moving another value into EDX, and then it's going to call the interrupt. So if you remember that from the previous video, this is just a simple syscall. We don't have to just track down the whole process. We can just take a look at the Linux table of the 86, specifically the 32-bit, and try to figure out what this syscall is doing. Okay, so we can go in here and see. So what do we have? Let me go back. So it's actually setting 3 into EX. So let's see, 0, 1, 2, 3. So yeah, so this is the 3. So it's a read syscall. So that explains why we have, when we try to run the binary, we are getting a prompt trying to ask us to write something. So this is actually done using this block. So this block is like doing that, and once the result is given to the computer is going next to set the EIX as the result, as the return the return of the result. Yeah. So this is actually just a simple syscall to the read. I suppose this is the address of the buffer, since if we'll take a look, so the EIX is the number of the syscall, the EBX is the file descriptor. As we can see, it's 0, that stands for the standard input. The ECX is the buffer, so this is the address of the buffer that our input will be redirected to. Um, we also have the EDX, which is just the count of the number of the characters that will be read from the keyboard. What else do we have? So 0x14, I think it is. Let me just check that out. 0x 14, so it's 20. So we are trying to read 20 characters from the keyboard, and then he is going to put the result, which, as we have talked in the previous video, the result of any kind of function or any kind of syscall is gonna be returned into the EIX. So the EIX will contain, actually, in this case, the number of characters, the number of characters typed in the keyboard. Yeah, and he will be moving that into EDX. We can check that out. We can check that out if we want. So we can just to step an instruction, guys. All what we have to do is just do SE. So SE stands for stepping. So yeah, we will be stepping. As you can see, once we are trying to step, we have, for example, we have done that. So we step two instructions. Let's try to see the EBX and the ECX, for example. So ECX, as you can see, have changed it to that value, and EBX have changed it to 0. So let's try to keep moving on along the code. We have now EDX 0x14. Now we also have the interrupt, and as you can see, he is asking for something to give. So we will be giving, for example, iron wide. Now, once we have done that, we should, for example, have into the EIX, for example, after just hitting the enter just to tell him, okay, that I have finished it, he automatically filled the EIX with 9. So actually, we have now iron byte, I suppose, at that address, since this is the address of the buffer, and we also have 9 into the EIX, which means that the length of our input is have been put into the EIX. So let's try to, for example, check the content of that address. So to check the content in GDB, we can just use x dash s, and then the address that we wanna see, just in the format of string. So x stands for trying to see the value in the memory, and s is actually specifying the format of the output. You can check more out the GDB cheat sheet to understand more about the commands. So as you can see, we have now iron biased with an empty slash or another dash n just um, at the end of this string. So what does that mean? That means that once we hit the enter to send him the input, the that character was added. So this is why the size of the EIX is not 8 but a 9. Okay, this is interesting. Now let's move on. So we have now transferred what's in the EIX into the EDX, and we have into set ECX to 0 and EBX to 0, and we are now okay. We are now moving a byte into the AL. So AL, actually, guys, if you don't remember, is the lowest part of the EIX register, which means that this is the first 8-bit of the EIX. So we are moving a byte from the ECX um, plus the address of the buffer. What does that mean? That means, for example, if you just imagine that address, for example, as a variable, I don't know, string, for example. So this is like saying to the computer, it's like saying we want to access the first character. Since the ECX is equals to 0, it's like saying to the computer we want to access the string of 0. So this is the equivalent of string of 0 in assembly. And then we are putting that value into AL. And then we are adding what's in the EBX with the EIX. Now, let's try, for example, to see that. So if we go and check the AL, we are seeing, for example, now that we are having um, 0x69. Since we are already having that, we are now seeing 69. Okay, what does 69 stand for? Let's see. 69, guys, should be standing for the I. So let's see. Sure, sure of 0x69. So yeah, so this is the I. So since we have passed iron byte to that address by just doing plus ECX, we are getting the I. Okay, that's perfect. So the AL now contains the I. So the EIX contains the I. He is adding what's in the EBX with the EIX. What does that mean? That means actually now that we are supposing that the EBX is equals to 0, we are now adding what's in the EBX with the EIX. If we imagine that, for example, guys, if I go into the notepad, um, what do we have? So if we suppose that, for example, let me just get that. Uh, okay, so this is better, yeah. Now, if we try to understand what this do exactly, so imagine the add ebx virgule comma, I'm sorry, AIX is going to do ebx equals to ebx plus AIX. Taking on consideration that the EIX contains actually the first character, so it's gonna be equals to the EBX, which is 0, as you can see, plus what's in the EIX, which is actually the I, plus the I. But actually, he's not going to sum. He cannot sum like a number with a character, but he's going to actually sum the ASCII of the I, which is as you can see, he already did that, which is the 069. So he is going to sum that, and the EBX should actually or should eventually have the 0x69. So let's try to see that. So if we do that, we see that now that the EBX, where's the EBX? Yeah, so we have 0x69 now in the EBX. Now let's move on. Now he is incrementing the ECX. He's comparing the ECX with the EDX. Taking in consideration what does the EDX is having. EDX EDX is having 9. So he is incrementing the ECX and he's comparing it with 9. And then he is trying to test, he is gonna be jumping if not equal to loop. What does that mean? It means if they are not equal, so if the ECX is not equal to the EDX, he's going to loop again. So by looping again, I think he is now eventually just implementing a loop that will be going to um, that will be trying to travel our buffer because the ECX is already incremented, as you can see. ECX now is 1, so he is going to access, as you can see, he is going to change the character now, which is 0x72. If we try to look at that character, so 72. So this is the R, this is the R, I'm sorry. So he is going to travel what's in iron byte. He is going to travel the string iron byte and try to see what's in there. And each time he is going to sum what's in the EBX or the old EBX with the EAX. So I suppose at this point we don't have to look more. All what we have to do is just execute that code. As you can see, let's see what the ECX now is. So ECX is 5. We complete. So the ECX now is 6, 7, 8. Now, okay, he is 9. And he is not going to take that. And the reason is because the Z flag is not equals to 1. What does that mean? The 0 flag. Okay, we'll see. Okay, so the 0 flag is not taken. So we move on. So we are not going to jump back to the loop. Now what's next? He is going to compare the resulted EBX with this number, which is 0x988. If it's greater or equal to that number, he is going to jump to the win, otherwise he will be jumping to the fail. So let's try to see, okay, so it's eventually, I think not greater or equal because the EBX is 0x376, which is, um, she's not greater than 988, so eventually he's not going to take that jump to the win. And as you can see, we are eventually going to be jumping to the fail function. The fail function is pushing two numbers, as you can see, and then he is calling another function, which is the print, and then he is doing a syscall using those two numbers. I suppose these two numbers should have something. So let's try to see what these two numbers are. We already have the stack in front of us. So he pushed you failed again, and he pushed another number, which is 18. I suppose this is the length of the message. And then he is doing the syscall based on these two parameters. And then he is calling the interrupt. And then he is returning just, they're just returning from that. Okay, this is interesting. What do we have now? Since we have already done all the static dash dynamic analysis, we can just conclude that we will be, he will be trying to do, for example, scan f, for example, percentage s, and the address of the string, let's say of the buffer. Once he done that, he is going to loop into all of that from 0 um to the length, I suppose. I is gonna be inferior to the buffer, the SCR length of the buffer, which is in here, which is in our case, if we try to disassemble the code again, um, start, which is in our case, as you can see, the AIX will be containing the EDX, and um, the check was always hold it on the EDX. So that makes sense. We can just use EDX, supposing that the EDX will be containing the length of the buffer, and just some pseudocode just to understand what is happening. E plus plus, and then I suppose he is going to loop through our buffer, and then he is going to do, he already initializes EBX with 0, as you can see. He initializes also, let's suppose in our case it's the ECX that will be looping. ECX, ECX, okay. So if the I suppose he also used disassemble loop. I suppose he used also the AL. So the AL will be containing um, the buffer of ECX, as you can see. This is the ECX and this is the address. And then he is going to do EBX equals to EBX plus EIX, because he is just setting the EIX also to 0 at the beginning. EIX is going, he is going here to um, change the first 8-bit, and then he is going to um, add actually what's in the EBX with the EIX. He is going to do that um, to the size of the buffer, and then if the EIX, the EBX, I'm sorry, is greater than or equals to exactly 0x99, we win. Otherwise, else we fail. This is actually how you can decompile code based on how you see it. Um, I tried in this video to do that manually for you, just to understand that there exist some compilers out there like IDA and Ghidra, but at some point you need to do their job at least once or two just to understand how assembly works, because at some positions you are not going to do everything using IDA and Ghidra. Sometimes you need some assembly skills just to understand what is happening. So yeah, so this is now what is happening. Just to break this and get into the win, we need to give an EBX that is superior to this number or equal, and this number generated using the sum of all the characters that will be given to the program. So to do that, let's try to maximize our chances just by trying, for example, to see the ord of the z, since I think it's bigger enough. It's big enough. So if we do this, for example, multiplied by 19, for example, I see this number is hex multiplied by 19. What do we get? So we get that. Let's try to multiply it by 20. Okay, so we need actually 20z to do this. So if we do that, we should be okay. Um, so if we send that to the program and we try to run that, so let's try to run that. So if you're trying to run that using this number of z, we should get the congrats message. So yeah, so this is the first challenge, and as you can see, it's a pretty basic challenge. You don't have to be too much an expert just to solve it. What matters in this challenge that we have learned how to read code both statically and dynamically, and how we can analyze from the GDB the different kind of states of, or the different states of registers. Um, what else? So yeah, sometimes you need to combine both your static analysis skills and dynamic analysis skills just to solve these kind of problems. Now, what's really interesting now that we will be moving on to the next challenge. The next challenge will be, let's see, let's start by running the challenge first. Let's see what is happening. So he is saying enter the flag. Let's see if we try to enter the flag. Okay, let's say flag equals. Let's have some random. Okay, as you can see, he's saying wrong flag. Let's see the file of the challenge. So it is 64-bit now. It's not a 32-bit, which means that the registers will start with the R. Now, as always, pause the video and try to solve it on your own, and then go back just to see with me how to solve it if you get stuck for sure. So we have an ELF which is 64-bit, LSB that stands for Little Indian, by executable, actually a kind of mitigation. This by is a kind of mitigation on binaries. It is dynamically linked, and this is the path to the interpreter. Okay, so also it's not a script, and this is just compiled using is compiled to the GNU Linux 3.2.0. I suppose this binary is compiled using the GCC, so yes. Now we might just have another format of assembly. It's not like the usual one since the previous one was assembled using NASM. I suppose this will have a lot of other features. So let's try to open up using GDB. Before using GDB, let's try to run strings. Maybe we got the flag directly. Who knows? Since I think the all the challenges that I have tried to make are easy and anyone could solve. So Shoal2, if we try to see the different kinds of strings, we have Shoal2, puts, glibc, okay. So you have find the flag and there is this flag. Let's write this one. There is this flag. Is there anything else? Yeah, as you can see, this is the compiler as I have told you, it's GCC. So string can help you a lot while trying to investigate this kind of binaries. So this is a pretty easy challenge just to solve. This is one of the basic challenges where you have to know that there is command strings. So yeah, so this is the flag. I suppose we don't have to go too much into details on how this binary works because I suppose the next binary will not be solved using the strings. So let's try to skip this binary since we have solved it and go to the next binary directly. So again, we try to run file on that challenge. So we have this in front of us, which is again an executable linkable file with a 64-bit architecture, which is Little Indian. I'm sorry. It's also a py. Okay, it's not a script and it's dynamically linked, and this is the path to the interpreter. Okay. Let's try to run strings on it. Also, we might get some informations about it. Yeah, strings. We have any show 3. So what do we have? So this is all the kind of sections that exist. We also have enter username, enter password. Okay, access granted and access denied. It looks like it's a kind of login, login portal or something like that. What do we have? Also, it's GCC. The compiler is GCC. Which means that it's a C program. We have a here compare string copy puts string length. Okay, we have scanf. Okay, this is interesting. Let's try to run it. Challenge 3. So username ironbyte, some password. What also access denied. Let's ramp and try to debug it again. So GDB um challenge 3. Let's see what we have. So let's try to disassemble that. So again, before trying to disassemble any kind of function, we also need to know what kind of functions that exist. So info functions to see the different functions that exist, and as you can see, there are a bunch of functions this time, not like the previous time. So there are pretty much functions that were generated by the GCC compiler that can be used. One of them, for example, he is now, for example, in this trying to map down the printf and this string, compare the puts, etc. Now, what's interesting in this those functions is the main, since it's the beginning of the program, and the start also. I suppose the start is going to be calling the main, so let's jump on directly to the main by trying to disassemble it. So disassemble main, so I think it's pretty big. So let's try to copy all of that down. Before that, let's try to let's try to decompile that code. Maybe we don't have to decompile. Let's just try to get it into my VS Code. Yeah, just for a better vision. Yeah. Okay. So let's skip the first instruction since it's not like an instruction to look at for now. Just skip this instruction for now. I will be trying to explain this instruction in the next video, and actually I have made some research on that. The first time I have encountered this instruction was with my teammate Monji, and we have tried to just research that in his room at that time. But I just get that in my mind, and I have done my own research on that instruction. You can just research it if you want. It's not like a big research. Just throw the instruction on the internet and try to understand it. But for now, it's a kind of protection um, for the main function, guys. So yeah, so now what do we have? We have so push rbp, move airsp into rbp, then push rbx, and then subtract that. So I suppose he is saving the rbx, the register rbx in the stack, and this is the function prolog, the usual one that you would have. Then we would be having move arrax, so he is moving some value from the file segment. At that offset, he is going to move that value into the air ix, and then he is going to move that value into rbp minus 0x18. So I suppose these two values are just to initialize something called the stack canary, which, as you can see, if you go down into the code, we see some call actually to a function called stack check fail. So this stack check fail, guys, is used to check if the stack canary is overwritten or not. So the stack canary is a kind of protection against the rope attacks or the return oriented programming attacks. You can check that out. It's something so cool. So rope attack is pretty famous, guys. Well, it's not about this series of reverse engineering, but you should be at least having some informations about this attack. Yeah. So one interesting thing is that if you see the previous video just by watching the crash course of the 86, you should be able to understand how this attack is implemented. So basically, it's based on the stack itself. So it's really interesting. What else? So this value is actually gonna be, as you can see, he is setting that value. um he's going to set that value above the base pointer, just as a way to make sure that no one tries to overflow the stack and goes into another location. So this is what the stack canary is used for. Now he is ignoring the EIX, and then he is loading some effective address, which is this one. Let's try to see it using the GDB, since we have access to the GDB. Let's try to get this one how like that, and this one like that. Um, yeah, this is better. Okay, so let's try to see this address. See what we have in this. Um, so this is into a username. I suppose if we track down the calls, we should be able to get um, every kind of call that is happening that would help us reverse engineer this code better. So this is going to call the printf, and he is actually not using the cdecl calling convention. Now he is using the 64 or the 8664 calling convention, just to look at that calling convention. So x64 calling convention rules. So the caller uses registers to pass the first 6 arguments to the caller. Yeah, I think um I have just got a mistake. I'm sorry, I got a mistake in the previous video. At the ending of the video, but I think I have said that he is going to pass the first 4 arguments on registers, and then he is going to use the stack. Well, I think I made a mistake there. He is going to pass the first 6 arguments to the callee, and then he is going to pass the other arguments on the stack. So yeah, so he will be using the RDI and the RSI to do that. So as you can see, he XOR the AIX to 0, which means he sets the AIX into 0, and then he tries to load the effective address of that string into the AIX, and then he moves that address to the RDI, and then he just initializes AIX with 0, and then he calls the printf. Now what's really interesting, guys, that the printf is going to return is going to print the characters and return the number of characters that was printed in the screen, and the return address should be and the return, I'm sorry, should be into the EIX. Now we also have another offset, which is the base pointer minus 0xe0. He's going to load that address into the AIX. He's going to move it into RSI, and then he's going to call another. I suppose this is another string. Let's see what this string is. So this is the percentage %s. So that makes sense. So he's going to do scanf. So as you can see, the RDI is having the percentage %s, and the RSI is going to be having the address or the offset of that variable on the stack. So this RBP minus 0xe0 is a variable on the stack. And then he is going to call the scanf, and then I suppose he is going to print another message, and then he is going to call another scanf, which means if we try to look a little um, into the code, we see that when we try to run the shell 3, we have username and we have set. So just by looking at these instructions, we can came to the conclusion that the ASD will be in this will be at this offset, and the set will be at this offset, which is the 0xa0. So just by looking at this block of code, we can just came to the conclusion that the ASD and the SAD will be at those locations. We can check that out if we want using the GDB too. Just by setting a breakpoint in the main. Um, did we set the breakpoint? I suppose no. Okay, break into the main. And just by running, we hit the breakpoint, and now we can just go step, 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 step. Now he's calling the printf. So to get out of the printf, we need to just to do finish. Now we are out of it. So now we continue step, 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 step. Now we have that. So we step again. Now we are into the scanf. Now we finish. Now he's trying to ask for a username. So it's ironbite. Let's see if ironbite is okay. So ironbite is also put into that register. Let's try to see now. Let me see. Let's try to see. This is the call, and this is the offset that we suspect that this one will be containing ironbite. So let's try to see it. So RBP, what is the RBP? What is the base pointer? So this is the RBP. Okay. If we try to subtract out of that, let's try to see it. CXC. Now what's in the EVP, if we can see like that. So this is an error, I suppose. Let's see if it's the right address or not. This is A0, so this is A0. Now if we try to subtract from it the offset 0xe0, 0xe0, okay, saying we cannot access that memory. Okay. Um, okay, let's suppose for now that this is gonna be containing the input of the username for now. Okay, let's continue. What else do we have? So let's continue. Is E, we jump, and then we print again. We finish that. Uh, Finish. Yeah. Now we go back to the main. We load, we load, we load. Now we need to scan that. See, DI. Now we are in the scan. Enter the password. For example, set. Now, okay, he is trying to, as you can see, just after scanning that, he is getting what's in the username. He is going to put that into the RDX, and then he is moving another offset, which is that into the RAX, and then he is copying. He's starting a string copy. So string copy, guys, takes two parameters. The first parameter is actually the first string to copy to, and the second parameter actually is the source string that we'll be copying from. So this is why the RDI contains the this address or this specific place in the stack, and this contains the source string, which is our username. So if we take a look now, we can just make some replacement, just using the addition. Let me see, additions, replace. We should be replacing 0x, e0 e0 with username. So this is better, and we should be also replacing that this one also with the password. Okay, xe0 with password. Okay, now this is better. That makes more sense. Okay, since now we have all these instructions, what do we have now? We are now trying to copy what's in the username. Let's call this offset also. I don't know. Let's give it a name. Um, Addition. Let's call it, for example, I don't know, string or a street. Three is better. Okay, three. Okay, yeah. So, let's go back a little back. So, what do we have now? So, we are copying the username into the string, and now he is going to move 0 into this place. I think it's another place in the stack since it's rbp minus 0xe4, so it's another place in the stack. Let's see, then he is going to be jumping um, into another place, which is the main plus 22, main plus 22. Okay, this is place. So he's moving that value into the AIX, and then he is doing a move SXD. So move XD is actually, guys, used, for example, when trying to move a register that is 32-bit into a register that is 64-bit. Actually, he is going to zero all the um, he's going to zero no he is going to put a 1 in the other half, which means the other 32 bit of the register RBX. Next, what he is going to do, he is going to move what's in this tree into the RAX, which means he is going to load the effective address of that tree into the RAX, and then he is going to move what's in the RAX into the RDI, and um, then he is going to calculate the length of this tree. And if the length actually is compared to the RBX, which is actually um, the same variable or the same offset on that stack. So that means that this is also a variable, so he is going to compare it with the RAX, he's going to compare it with the length of this tree, and if it is below, he is going to go back into the main plus 165, which is this one. So this is actually an implementation of a loop, and as we can see, this is how he is going to implement a loop. So this is another implementation of a loop. So now I suppose we should be able to just um, track this loop down using again some static analysis just to understand what this loop is doing. So he is getting that value. He's moving that value into EIX. Let's ignore the CDQE for now. He is now moving, instead of SX, he's going to move ZX or ZX. So ZX is actually, guys, um, instead of setting one to the other half, for now we are trying to move a byte into a 32-bit register. So to do that, we are going to move that byte into the EIX, but we will be setting the other half, or the other let's say 16 plus 8, which is let me see how much 16 plus 8 is. It 24? I'm so bad. I'm just calculating these numbers. 16 plus 8. Yeah, 24. This was, my guess was right. Yeah. So the other 24 bits of the EIX should be equals to 0 because of this Z. So this is a kind of options that you can add to the move. You can search for that on Google if you don't know, but as I said to you, move ZX is going to be putting one byte, which is in this location. He is going to do move that one byte into the EIX, and he is going to zero the other parts of EIX. So what is exactly that he is doing? So he is taking the ARIX, which is already pointing to that variable. Let's call that variable. I suppose this is the counter. This is how you make um, some changes that are really, really important to the code to make it more legible for you, or more readable. I'm sorry. So let's call it the counter. So 0x4 counter. So this is the counter. Okay. So he is moving that value of the counter into EX, then he's doing like RBP plus minus string, so the other string that was already initialized to something. We have already initialized this string to the username. So he's doing RBP plus RIX multiplied by 1, which means that 1 is actually just useless because he is trying to multiply it by 1, plus RIX minus string. If we do like this is better. Plus RIX, and this one plus RIX. Now that makes more sense because now he is trying to access the string of RIX, which means that he's trying to access the current character at that specific string. Now that makes more sense. Now, now what do we have? So the RAX will be equals to 0, and then he is going to increment the AIX by 1, and then he's going to move that value into EDX, then he is going to move again the value of the counter into AIX, and then he is going to move the DL, which is actually the add is going to add what's in that current character, and he's going to add 1 to that character. Okay, and then he's going to save the result into EDX, and then he's going to move the counter into EX, and then he's going to move the result of the current, or the other one of the current, or the I'm sorry, the previous operation into the current character. And then he is going to add 1 to the counter, and then he is going to move that counter again into the AIX. Okay, so now that makes sense. I think we can just decompile that code now, as we have did with the other one. So if we try to decompile this code, actually, guys, so the first thing that we said he is going to do, so he is going to scan for the username, and then actually he print first, so he print the username, and then he scan for the username, and then he print message for password, and this is a message for username. What else do we have? So he's going to scan for a password, I think. Yeah. What do we have? So this is the password. Yeah. So once the username and the password is done, he's going to str copy uh, into the tree the username. So what does that mean? That he is going to set this tree equals to username. This tree equals to username, yeah. Now, once we have done that, he's going to start a loop. The loop is just going to be looping through this tree. So to loop through this tree, he's going to do for e that is in this tree, and then he is going to loop through it. So the first thing that he has already done is that he is in this place. He is loading that into the AIX, so he is loading AIX equals to 3 of um, of the counter. Let's call that as a counter. That is equals to 0 counter that is going to be inferior than the length of this 3 counter plus plus. If you go use that a little, okay. So he is going to do that. So the AIX will be equals to this 3 plus AIX. Yeah. Just taking in consideration that the AIX in the previous line was equal to, as you can see, the AIX was equals to the counter. That's why this we have AIX, which is the same. AIX. I'm just trying to mimic the code that is in there, just trying to decompile it on my own. Um, so what else we have? So which is the same as 3 of counter. So that makes sense. What else do we have? So now we are adding it's what's in the EIX with 1. So if we do the add, so EIX equals EIX plus 0x1. So he's like saying 3 of counter 3 of counter plus 0x1. Yeah. Then he is moving what's in the EIX into the EDX. So EIX equals EDX, which means that he will be equals all of that. So EDX should be equals to that. Okay. Now the EIX is gonna be equal to the counter. Okay, so EIX equals to the counter, and then he is going to move what's in the DL, which is 1 byte, into the string. Okay, that means that he is going to string of counter, which should be equal to DL, which is, if we look at the EDX, which DL, because DL is part of the EDX eventually, so he is going to be looking like that. So string of counter is going to be string of counter plus 0x1. Now, so I think that makes sense. So now, by using this loop, he is going to be changing the value of the string that was first initialized as the username. So eventually he's trying to change the username by adding a 1 to each of their characters, I suppose. Yeah. And then he is going to be adding the counter, which is already been done just by using that. And then he is going to move that into EIX, then moving that value into RBX, then loading again the address of the string. Again, he is trying to get the length of string. Okay, okay, okay. So yeah. So this is what the loop is gonna be doing. So now once we are out of the loop, I suppose he is trying to load what's in the password or the address of the password into RDX, and then the other address of this tree into the REX, and then he is moving them to the register that will be passed as parameters to the str compare that will be comparing two strings, which are this tree and the password. So he is going to be generating another password based on the username. So what this means that each username will be having a generated password using the username. So just to see what is going to be happening next. So if he is going to test, so the test command, guys, or the test instruction is going to be trying to see if the AIX is equals to 1 and the AIX is equal to 1. If both of them are equal to 1, then um, we will be jumping to this block. Let's see this block, what this block is gonna be doing. So let's try to see now that. So x slash s. I think the addresses are not the same. Let me just disassemble main. Disassemble main. Yeah, the addresses are not the same. That's because of the byte. Oh my god, I'm so sorry about that. Yeah. Okay. X. What? Let me wait a sec. Ah, okay, okay. I missed that. I'm sorry. Sorry, I missed that. It's that's not the full address. Okay. Yeah. So this is the access granted, and this is the access denied, I suppose. Yeah. So I suppose this is the access granted and this is the access denied. And once we are now at this position, once we complete the conversion between the string tree and the string password, we should be able to know how to do that. But we have already reversed the code and find out that the string is gonna be generated using this way. So it's gonna be a string of counter, which is just the string of counter plus one. So to solve this problem, all what we have to do is just give him a username, and then the password is gonna be just um, each one of the each character of the username is plus one. For example, if we do ABC, if we do BCD, we should be having access. Yeah, otherwise we won't have any kind of access. So it's a pretty basic challenge just for someone who is completely new to reverse engineering, but this is just one of the few challenges that can let you just learn how to do this stuff. So if you have learned something new, don't forget just to subscribe. If you didn't learn anything new, it's okay. Yeah, so I think we have hit the end of the video. If you have any kind of question, you can message me on Twitter or leave a comment below in the comments sections. And yeah, I think we had fun today. So see you on the next video. Bye.